I'm going to show how to make this inverse squared pattern using Affinity Photo's Procedural Texture Filter. I believe this pattern can be traced to Inigo Quilez originally, who is pretty famous in shader programming. He wrote Shader Toy, or helped co-develop Shader Toy, and he's done a lot of work for big companies like Pixar and places like that. So a pretty good, excellent programmer, and he has some excellent tutorials online. I'll put a link to some of his stuff in the description for this video. This pattern is pretty simple, but it's very interesting. And so this is really based on the inverse squared, like 1 over r squared, and a lot of physical laws are based on the inverse squared law. For instance, the intensity of light as it propagates from a point source decreases as a function of 1 over r squared. The same as the intensity of sound from a point source, because it's moving out in sort of a spherical fashion, and so it's decreasing as it moves out. And so a lot of stuff, even in charge of particles, like 2 charged particles or gravity, a lot of things in physics follow the inverse squared law. This pattern is based on the function v.v. And at first I was pretty confused by what was going on here. But then when I dug into it a little further, I realized that if you remember, the dot product of 2 vectors is the magnitude or length of the first vector times the length of the second vector times the cosine of the angle between them. If you have v dot v, the angle between a vector and itself is 0, and the cosine of 0 is 1. So that term just goes away, and so then you just have the magnitude of the vector times itself, which is the length squared of the vector. And actually, in the procedural texture filters, there's a function that gives the length squared. And so I could have just used that, but I decided to stick with v.v in this example. The other thing I'll do later in the video is, if you look at this part in the middle, there's this sort of wild stuff going on, and that is called aliasing. Aliasing is when your sampling rate is less than the frequency of oscillation. And you can run into that in a few different situations. If you ever saw an old movie where a wagon wheel was spinning and appearing to go backwards, that's a typical example of aliasing, where the projection rate of the images is slower than the rate at which the wheel is turning. Another example is in audio. If you have high frequency audio and you're sampling that digitally, you can end up with some weird sort of overtones that come in and create artifacts in digital audio. In this case, we're looking at the alternation of the pixels. So our minimum frequency would be 2 pixels, and so if the frequency is higher than 2 pixels, then you have aliasing in the image, and it makes sort of a noise in your image. And so Inigo Quilez talks about how you can get rid of aliasing on his website, and I'll put a link to that. And I'm going to do sort of a simplified version of that. So it's not quite the same, but it maybe gives you sort of the idea of what to look for and how to start addressing that issue. Now, this is a fairly easy to implement filter, but if you add on the anti-aliasing, it'll get a little more complicated. I'll start with a new document. I will choose XGA, but change it to 1024 by 1024 pixels, and make sure it's in RGB mode, and create that, and I'll fill it with black. I'll add a live procedural texture filter. I'll add a single equation and assign it to all 3 channels. I'm going to add 2 0 to 1 range inputs, A and B. I'm going to call the first one zoom in, and the second one zoom out. And I'll use these to control the scaling of this. I'm going to start with variable coordinate vector v equals vec2 of the relative x and relative y coordinates of my image. I'm going to multiply that by a and divide by w, and I'm also going to divide by b. So that looks like that. And so if I change this, if I bring this down, it will sort of zoom in, and if I bring this one down, it'll sort of zoom out. To prevent this from going all the way to 0, I'm going to add a clamping value to this, and I'm going to use a real input, and I'll just leave it at C. This will be the clamp minimum. And I don't really need to do this, but just for point of reference and to prevent a divide by 0, I'm going to do this anyway. And so instead of just A, now I'm going to modify this and use clamp min of A comma C. And then also for this B, instead of just B, I'm going to use a clamp min of B comma C. Okay, so that way when I bring this all the way down, it's not going to disappear completely. And the same with this one. Alright, next thing I'm going to do is set up another variable system. It's going to be V1, and it's going to just be V divided by the dot product of V with itself, V. And it looks like that. And now when I zoom out on this one, you can see it has these two circular areas like that, but it's getting more, these values are going up above 1 over here. Okay, so that's the coordinate system. So next I'm going to just apply this with an oscillator. I'm going to use oscillator, an H oscillator based on the sine, and you can try other oscillators. They'll all give slightly different looks, but I'm just going to use that one. And so I get that, which is sort of a fun little pattern like that, but I like this even better if I take the absolute value of it. There's the pattern. I'm going to add a gradient map to this, and it's one I developed for, I was thinking of corroded brass when I did this one, but I like that one really well, so it looks like that. And I'll just go over this gradient map, so if you want to use the same one, you can if you want to. Anyway, let's see, so starting over here at 0, I will use the hex value, so it's C85019. Then at 36%, I have 287960. And I go up to a little bright spot here at 42%, and that is 22D6A5. And I have sort of a dark edge coming in over there. That one is 221304, and that's at 48%. Then over at 57%, I've got 673B0B. And I'm making it a little lighter, 75%, it's 9C6A0C. At 86%, I have sort of a gold color, and that is F2A81C. Then sort of a pale gold, and that is FCCE8D. And then at 100%, I have F3E4AB. I can drag this down on top of my filter so it's all in one layer. And then I can try to zoom in. And you can see the aliasing occurring in here where these little phantom patterns start showing up in the regular pattern. And then this is the zoom out. Now to get rid of this aliasing, if I wanted to do that, I'm going to add two 0 to 1 range input sliders, and these are going to be on a smooth step function. And I'll call one BL0, call that band limit 0. And the other one will be BL1 for band limit 1. And then I'm going to create another real input value, and I'm going to call this one the event horizon, just for fun. I'm going to set that at, I'll just start out at 1, but I'll bring that up later. To create the band limiting effect, I'm going to insert another variable in here. I'm going to call it BL for band limit, and I'm going to use the smoothstepn function with BL1 and BL0 as the inputs. And then I'm going to look at the coordinate system, and I'm going to base filtering this on the coordinate system. So I'll just look at V1, and then I'm going to multiply my other function by BL. So it will fade it out when the frequency gets too high, and I'll just adjust this manually. So when I did that, I found out that, oh yeah, you cannot use a vector with a smooth step function. So first thing I thought I'd try was changing this to an X, and there's that one. And then I needed a way to, it's filtering out way too much stuff, so I needed a way to make that smaller. And I can do that by dividing this by my event horizon, D, like that. And so now as I bring D up, that gets smaller and smaller, and I can go till, you know, I'm just filtering out the stuff that's aliasing down here. And then I can, this will now control the band limit a little better, and this one is controlling the smoothness, whether it's a sharp edge or a smooth edge. And I can just go until I get rid of all the, you know, all the aliasing on there. Now that's X, and I need to do both sides of this and then Y. So in order to do that, first of all, I'm going to take the absolute value on this v1.x, and that should pick up the other side. Okay, so there's that, and then I'll do the same thing for y, and I'll multiply these together. So I'm going to copy this whole smooth step function and paste it here and multiply. And I'll change this from an x to a y. So now I'm filtering out the aliased stuff down there in the middle. I can make this, you know, until it goes completely away, or bring it up until I just have, I don't have any aliased oscillations down there. And I can sort of smoothly transition, and you can see probably here if I bring this up more, eventually I'll get back to the aliasing again. It's not exactly the way Quilez does it, but I thought it was sort of an interesting topic to bring up, that you can get aliasing in your procedural texture, and there are ways to eliminate that aliasing. There's probably more sophisticated ways than this, but this is the first thing I came up with when I started looking at that. So that's what I'm calling the inverse squared pattern. Let me know if you have any comments or questions, and thanks for watching.